All right, this is the Snell's law screencast one last time. It has to be the last, and hopefully this time it's perfect, or darn near perfect. Anyway, so I'm going to go through the whole derivation again, and this time hopefully I got those misconceptions really worked out. I looked through them, and hopefully that effort pays off. A few things. So first of all, here is a simple diagram, and so we have incident and we have transmitted light, or transmit or two different incident indices of refraction, which, as we learned in chapter two, that just means that the interaction between the surface and how it and the way that it interacts with something's electric field is different. It just so two different indices of refraction there, and what we've got is so we've got some light that's reflected and some that's transmitted into the other index into the other surface. Obviously, E is perpendicular to K. There's P light, which is perpendicular within the plane, and then there's S light, which is perpendicular outside the plane. S light's the only light that goes into the X hat direction. The other two are the only field, I should say, that goes into the X hat direction. The rest of the field stays in the Y, and the Z is the P hat. That's going to be important coming later. So here is our unit vectors for our vectors for incident, reflected, and transmitted light right there. As you can see, these are vector functions, and one of the mistakes I made when interpreting that, I'll talk about it in a little bit. It's a y hat and a z hat. Now, when we talk down here about you've got the EIKR minus omega t. Now it finally turns in now r equal. Anyway, I'll get into what r equals in a little bit. But first, let me show you why this is true. If we've got our k vector at a certain angle from our interface, or from the from the z-axis, I should say. So then the direction here is sine theta y hat plus cosine theta z hat, and there you've got it right there. And it works the same way for all of these. The only reason why that one's negative is because reflected light travels negatively in the z hat direction. So that's what gets us there. Now, so electric field is initial electric field times e to the I kr minus omega t. All we're doing here is we are taking we're partitioning out P electric field and S electric field in that part, and then we're substituting our K dot R. So let's deal with the K dot R first. K dot so our R is x hat plus y hat plus z hat. Because the and because there's no x hat, that term is extinct. But so therefore the y hat combines with the y sine theta, so it y hat sine theta, I should say, to give us y sine theta, and then our z hat combines with our z hat sine theta to give us z sine theta. There are no directions left. So what I've said before in a previous screencast about how about how I don't know what I said, but it was wrong. So anyway, that gives us that minus omega t, which is so that is kr omega t, which we got directly from there, and multiplying it by the partitioning out of the r vector. Now, what's going on here? Well, we have divided up our electric field into two components. We've got P field and we've got S field, and we've got so P is going, as I said earlier, P is staying within the plane and S is staying outside the plane. So let's deal with the S first, since that is it's simpler. Since the only S in the X hat, since electric field in the X hat direction is by definition S field, that's why x hat EIS, because because there's nothing else, no x in the p and no y or z in the s, so that's very nice. But our p is some combination of those two. Let's talk about the vectors. So we've got so in this case, simply by an argument of symmetry, what we've got going on here is we've got so this angle translates in the same angle right there. All we did was just rotated the vectors perpendicular 90 degrees, and that's that. So what are the components of our P electric field EP? I, and that would be, so first of all, in the z hat direction, we're going negative, you can see, and then so that would be negative sine theta z hat plus cosine theta in the y hat. And that's exactly what we've got, and we can do the exact same thing for each of these other vectors, and that's what they've done to give us these nice equations. Now, that leads us down to this next paragraph, which there's so much jam-packed in that paragraph that it's going to take some explanation. One thing that I want to talk about is pinch-off. Now, pinch-off, and as I talked about in my previous screencast I submitted last night, is that, so we got two things going on. Z equals 0. So z, we're just arbitrarily dealing with the field at the position 0. That's which is nice, because what that does is it takes out the z term right there, and we can get rid of that. So we don't have to worry about that vector. However, pinch off, as I said last night, is different. Pinch off, what that does is it's saying that that our dz, the delta z, is also approximately 0. And what I didn't explain last night is why. And by some combination of Faraday's law says E equals dB, negative b dB dt. And then all we're doing is we're applying, is that we're integrating that or summing that up. And then this is an example of the divergent. We're using the divergence theorem for the equivalence. We're taking, the magnetic field is all of the magnetic field inside this little box, and then our electric field is the circumference, is the not circumference, but the perimeter, or there's probably a better word for that, but it's the boundaries. So we can add up. So the reason why divergence theorem works is because the amount of light, that is the amount of electric field inside the box, is the exact same amount that is on the on the surface. So that is, so anyway. So that's what we're doing there. I believe I explained that right. But anyway, by pinching it off, because by adding electric field, we have to add some z and some y, and that's exactly what we're doing in this argument right there. Is that we're adding some y and z electric field. But if we pinch it off, where am I? We pinch it off right here at z equals 0, so we're at z equals 0, but we pinch it off, we can literally get rid of all of that z out of our off of the from the calculation, so that all we're dealing with now is y cosine theta. Theta, and we don't have to worry about the sine function, the z sine function, at all, because we've pinched it down using the divergence theorem and Faraday's law. So now we're here. Now, so what we're saying, because we've done pinch off, we're saying that the parallel components, the y-axes, on the left is equal to the parallel components on the right. We don't have to worry about the perpendicular components that we had before. So, so therefore, the parallel reflected plus transmitted, That's that right there. Reflected equals the amount. Excuse me. The amount incident plus reflected equals the amount the electric field on the transmitted of the interface, and that's why we have this equality there. Now that is a very complicated. So that is a lot for a simple paragraph, and it tries to explain all of that in that paragraph, say why we can do that, which I never would have gotten without all of this feedback and instruction that you have provided, Andy. So now we get to we're trying to make the argument that omega has to equal omega, has to equal all omegas have to be the same, and all k sine theta is the same. Because now, if that's true, which it is, but if it's true, that means that then quickly allows us to derive, first of all, that all speed of light is the same color. That's what that tells us. K is n omega over c. So and then all the c's would cancel out. So we're left with sine theta n sine theta I equals nt sine theta t, and also by consequence the law of reflection, which is because our n's are the same in for incident and reflected light, so therefore angle in is angled out. But this has to be true. This has to be true for that to be true. So what does that mean? That means that that by necessity for any y and for any t that has to be true. So we use the phasor diagram, and I looked up some stuff about Euler because that's essentially exactly what we're using. E to the I, a bunch of crap, and obviously the magnitude of this vector, and let's say that this is the x vector. The x vector, each of these are x vectors. We've got one vector plus a second vector is equals a third. The thing is that the magnitude of the vectors is not going to change because the or let me repeat that. The magnitude of the vectors is not going to change at a given z position. So regardless of where we are for where y is, and no matter where time is, the magnitude of the vectors are not going to change. What can change, though, is that these vectors can rotate, so that we are and that's exactly what wave functions do, is they rotate. They don't get bigger, because that again would imply that at a given z position, that somehow that we're increasing and decreasing electric field. That's not true. Electric field is the same at the same z. That's really important that was really important to my understanding of this. Instead, what's happening is that in this case, so for at a certain time, if we turn time on, that would make this thing go clockwise. If we have to rotate it, oops, there we go. This is not rotating the way I wanted it to, but that's okay. But basically, it's just rotating. And however, let me ungroup this now. Ungroup. And they need to all rotate together. All the vectors need to rotate together. So that's really an argument for the fact that our omega has to stay the same, which omega is how many radians per second is it going. And that same argument applies for we would be going the opposite direction then for the k k sine theta, or the ky sine theta. So then it would be we would just be rotating to the right, to the left. So again, we have to keep these vectors the same. They have to be rotating together by keeping our frequency, our angular frequency, and our and by keeping our k sine theta the same. Otherwise, we are not going to keep that the same, and this is going to end right now.